Hello friends, welcome back to my YouTube channel. This is Ramdas Pandit Bharsat, working as Assistant Professor in Chemistry at Maratha Vidya Prasarak Samaj, Nasik. In this video lecture, we are going to study about exergonic and endergonic reactions. Okay, so what is meant by exergonic and what is meant by endergonic, that we have to see in detail. Okay, so first of all we have to see about the exergonic reaction. You will see the meaning of exer. Okay, so exit, something is going out from the one of the system. So you will see how the reaction that have a negative delta G 0 where the energy is released are called as exergonic reaction. If you consider any kind of reaction and from this reaction some energy is releases, okay, the energy is going out, okay, so that time we can say that is the exergonic reaction. Okay, for example, you will see a reaction for formation of water from its elements. We have know in the water hydrogen and oxygens are there, so hydrogen and oxygen molecules are combined. Okay, so after the formation of water molecule there will be the some energies releases. Okay, so that is the exergonic reaction. You will see the second reaction, that for formation of carbon dioxide from its elements. Okay, so in the carbon dioxide carbon is there and oxygen is there, so we require for the carbon dioxide formation carbon monoxide and oxygen's molecules, right? O2 molecules. So formation of carbon dioxide, you will get reaction. Okay, energy will release energy there. So during the formation of carbon dioxides you will get the energy, so this is also exergonic reaction, right? So this kind of compounds are thermodynamically stable with respect to their elements. Okay, so in this kind of the temperature is carried out for this kind of reaction. Now we have to see the next, that is second type of reaction, that is endergonic reaction. Okay, so you will see the meaning of endergonic. So you will be the, and guess, the energy is coming from the outside to this kind of reaction, right? Now you will see the reaction that have positive delta G 0 where energy is absorbed are called as endergonic reaction. Okay, whatever the reaction is there, so for that kind of reactions require energy for the carried out, right? And there will be the positive sign for the delta G 0. For example, you will take the formation of diamond from graphite, so there will be the that much amount of energy. Okay, delta G 0 is equal to plus 2.9 kilojoule mole per, okay, per mole. Okay, so that much amount energy is required for the formation of diamond from the graphite, and that is delta G for the formation of compounds from its elements is positive. Okay, this means that these compounds are thermodynamically unstable with respect to its elements. We have know when any kind of reactions energy is required, so there will be the thermodynamically unstable reaction. Okay, and energy getting out from this specific reaction, so there will be the stable reaction, right? So it will be the exergonic and this will be the endergonic reaction, and these compounds cannot be formed directly from its elements, and these compounds must be synthesized by the alternate routes. Okay, alternate, there is no any kind of fixed route for the formation of this kind of compounds, right? Now we have to see the example based on this topic, right? In that the first one you will see calculate The standard gives free energy of formation of HI, okay, in the gram at 25 degrees Celsius from its standard molar entropy and standard enthalpy of formation delta S0 F is equals to 0.0832 kilojoule per Kelvin and delta H0F in bracket HI in gram is equals to 26.48 kilojoule per mole, right? So you will see the solution for this kind of reaction. We have to calculate standard gives free energy, okay, of the HI at 25 degrees Celsius temperature. So we have to know this reaction. So that is half of H2, right, in gram plus half of I2 in solid. So it gives, you will see HI in a gas form, right? HI in a gas form, right? So here will be the, we have to apply the standard gives free energy equation, so that you can write in this way: delta G0 F is equals to delta H 0 F minus T delta S 0 F. So you have to put values which are given here, okay? Delta is 0 F is given, okay, and delta HF0 is also given here, right? And the temperature for the Kelvin, okay, this temperature is given, okay, but we want temperature in Kelvin. So 273 plus 25, so you will get 298 in a Kelvin temperature. All right, so you will take this value from here, right? 26.48 kilojoule per mole minus, right, minus, and T in Kelvin, okay, capital T is given, so we have to write in a Kelvin, right? And we have know how we can form the 273 plus 25, you will get 298 in Kelvin temperature into, okay, and the delta S0F, this value, okay, 0.0832 kilojoule per Kelvin. Now after calculation you will get 1.69 kilojoule per mole. So that is the standard gives free energy for this reaction, right? HI in a gas form. Now we have to see the next example, that is second. You will see that potassium chloride, common oxidizing agent in fireworks and match heads, undergoes a solid state. So the disproportion reactions when reheated, calculate delta G0F at 25 degrees Celsius for this reaction. Okay, again we have to calculate delta G, okay, delta G0F. So this kind of reaction, you will see again we have to form potassium chloride, that is the molecular formula of the potassium chloride, that is ACl, okay, and common oxidizing agent in a fireworks, okay. First of all we have to write the given data, okay, which are given into this example, into this problem. So we have to write in this way: given data, okay. So delta G0F values, KClO3, that is 269.3 per mole, and for the KClO4 is equals to minus 303.2 kilojoule per mole, and the KCl is equals to minus 409.2 kilojoule per mole, okay. So this data data is given for this example. Now you will take for this reaction solution is given 4 KClO3 in solid state. From this you will get thrice KClO4 plus KCl in solid form, right? You will see here 4 potassium, here will be 3 and here will be 1, so it will be the 4, and Cl thrice and here will be 1, so obviously it is okay. And how many oxygens are here? 12 oxygens are here, right? Now you will see next this equation, right? We have to calculate delta G0F, so we have to write this formula for this kind of, okay. Now delta G0F is equal to summation of NP delta G0F for the product minus summation of NR delta G0F for the reactant, okay. So the P stands for the product and the R stands for the reactant, delta G0F. Now we have no reactions and some data here, okay. So we have to put this value into this equation, and we have no the product, okay. So this will be the product and this will be the reactant, and the product we have to write for the first of all for the product. So how many moles? KClO4 3 moles, so we can write here 3 into values will be there, KClO4 that is minus 303.2, so you will write here kilojoule per mole here, and plus, okay, plus 1. Now this KCl, okay, KCl, and into minus 409, this is for the KCl, okay, 409.2 kilojoule per mole, and the next one is minus summation of this reactant, okay, reactant, this will 4 KClO3, so you will write here 4, okay, sub coordinator 4 into value for the KClO3 that is this 269.3, so you will write here, okay, 296.3 kilojoule per mole, and after calculation you will get that much energy, that is minus 134 kilojoule. So this will be the delta G0F at 25 degrees Celsius, okay, for this reaction. Now we have to see the next topic, that is chemical equilibrium. We have no equilibrium means the same amount of reactant and product will be present in the reaction. So we have to see in detail about it. Now the reactants are quantitatively converted to products, and that the amount of limiting reactant is negligible. That means if you will take whatever the amount of reactants, okay, in the particular reaction, so whatever the product of this reaction, so whatever the amount of reactant will be there, that much amount will be the product will be there, okay. For example, you will take here NO2 in gas form plus NO2 again in a gas form, so you will see here two nitrogens are here, okay, in the reactant, N and En, okay, and oxygens here is 1 mole and here is 1, so it becomes 4 oxygen, here will be the gas, okay. So you will see the same quantity of reactant and the product, right? Now the reaction has not gone to completion and attained chemical equilibrium, right? It states where the concentration of all the reactants and the products remains constant with the time, and that's why we can see it is observed that most of the reactions proceed to the completion at specified condition of temperature and pressure, right? And we can also say the many chemical reactions that stop much before completion, that we can see here. That is the best example for dimerization of the nitrogen dioxide, right? In this case, actually you will see the reactant NO2 is a dark brown gas and product is N2O4 in a gas form again, that is the colorless. And when NO2 is placed in a evacuated seal gas glass vessel, it is found that the initial dark brown color, okay, decreases in intensity as is converted to the colorless N2O4. So it is the dark brown color, okay, initially dark brown color, okay, it will converted into the directly into the colorless, okay, N2O4. So the however, even over the long period of the time the contain the glass vessel do not becomes colorless. So the reactions takes place in both the directions. The rate of forward reaction becomes equal to the rate of backward reaction. Hence the chemical equilibrium is not static but it is the dynamic. Static means the stable and dynamic is not stable, right?